This talk is about the transmitter chain. You have seen many talks, and I see much more brain went into the receiver than the transmitter. And if it comes to the transmitter, much more brain went into, say, SSB than went into telegraphy. And what I want to talk about you is how to get a pure telegraphy signal, because it turns out existing SDR technology is somewhat lagging behind. The quest for a pure transmitted signal has been with us in SDR for years. And most of the work has been done, say, for SSB. Adaptive pre-distortion was a landmark achievement, so the street name is pure signal. And surprisingly, very little effort has been invested into how to improve the telegraphy signal. If you look at the FPGA codes, this is what biologists would say a highly conserved part of the code. So it has been coded in 2004 and has not been changed since then. And recently, the Americans have launched what they call the Clean Signal Initiative, and this also defines goals for how clean a CW signal should be. And of course, we should take the challenge and fulfill their requirement. So if we can't do this, no one can do this. This is a picture from their homepage, and these red lines, they define what they call the goal. So what a CW signal should be about. It should have, in a given bandwidth, it should not exceed a certain value. And my feeling is that is not ambitious enough. We should be better than that. We should have a definition how far we would like to go down if we go, say, 1 kilohertz beside our signal. And my suggestion is we should have less than 80 dBc if we are farther away than 60 hertz, 100 and 120 if we are really far apart. So where do these numbers come from? My goal is if you have a S9 plus 60 telegraphy signal, then 1 kilohertz besides this, you should not hear this any longer. And then you need these figures. Well, this leads me to the question, I'm an amateur. I do have a spectrum analyzer, but this spectrum analyzer is low cost. So the question is, how can we amateur, how can I measure this? So the dynamic range of the gear I can afford is not sufficient to really tell if the signal is 120 dB below, so the bandwidth is about 80 dB. So I used my radio, it is an ANAN 7000, to measure its own transmitted signal. So I just took the feedback signal, which is used for pure signal anyway. And then I made a lot of experiments how to measure this. So you have your spectrum scope, and you can do some measurements, but it turns out if you want an accurate measurement, you have to dump the IQ signal which comes from the radio to a file, and then take this data and process it in a mathematics program. I use Mathematica, but there are free versions like Octave, or if you have MATLAB, you can do this. So I modified my SDR program to dump the IQ signal directly to a file, and then I took this and did a Fourier transform of that. And with an output set to about 5 watts, that is 38, 37 dBm, and the internal coupler of my ANAN, which is about 50 dB, I get a feedback signal which is slightly below the ADC limit, so that is the best measurement range you can have. So the first question is, can we measure this? And to this end, I just pressed the tune button. I just pressed the tune button and looked at what comes back. Because this fall off determines what I can measure. And from this picture you see, well, if I look at a real CW signal, then I should be able to measure its quality because this noise floor is low enough. And this is a part of the talk where it splits between mine and Laurence's talk, because this was a spin-off of his talk. He said, well, what about this? This is not only the noise floor of the transmitter. This is a combination of everything. It's a noise floor of the transmitter DDS signal. It's a noise from the preamplifier. It's a noise of the PA Then it comes to the coupler, it comes back. It's the noise from the preamp in the receiver chain, and then the intrinsic noise in the whole receiver front end. So the TX signal is better. This is what comes back. So then I did the experiment. The experiment is, I attach the Morse key to my Annan, I press the dot pedal at 24 WPM, and this is what I get back. This is the measured signal. You see, if I have 24 VPM, that is WPM, then the dot length is 50 milliseconds. That means this is a 100 Hertz signal. You get here at 10 Hertz, 30 Hertz, 50 Hertz, or so you get a peak. So this is measured. And if I compare this with what I want to have, then I see, well, at these points, it's fairly good. You see here some violations, but by and large, the CSI mask is met. But at large frequency offsets, I'm much worse than I want to be. At the edges of the plot, the signal is way above my target, which is the red line. So we want to be better. One good thing at this point is I advocate doing measurements. But in principle, you can do a Fourier transform of the pulse envelope, do a mathematical simulation, and you get exactly the same results. So this I find very rewarding at this point, that a mathematical simulation gives me the same result as my measurement. So where does this all come from? This, of course, comes from the pulse envelope of the telegraphy signal. If you had a hard keying, this is this dotted line, then you know, hopefully you know, then you would produce clicks which can be heard all over the band. I think if you are older, everyone has once in a life heard such a signal. And all the good thing is now in this shape of the envelope of the CW pulse. This shape mathematically determines the spectrum I showed on the last page. So I do not claim that I reinvented the wheel. I have to remind you that others have put forward this question long ago. This is the earliest article I could find on this. This is from QAX in 2006 from Alex, and he already taught us in principle how to improve. The important point is it has not happened, okay? Therefore, I do these experiments. So what is this all about? This is a shape, this looks like a cosine, like a raised cosine. So this is a standard shape used in the FPGAs. And this is a function Alex is putting forward. It's an integration of a so-called Blackman-Harris window. The problem with Alex's article is that he pushes forward an awfully complex algorithm how to calculate this. This comes from how it is done in digital filter implementation. But if you look at this algorithm carefully, you see it's a numerical integration. If you do this integration analytically, it's a function as simple as this. And you see these two, I call these ramps. This is the switching on of the CW signal. They are very different. This is a gradual switching, more or less, and this comes very flat out, then it switches on much steeper than here, and then it ends very flat. And what I will show you is that the behavior at small frequency offsets is in the raising here, and the behavior at large frequency offsets is in the gradual increase here. This makes a difference. So about 10 years ago, I implemented in the software Pi HP SDR, I implemented CW there, and there I used this shape, and I remeasured this today, or I remeasured it a few days ago. I get this spectrum. This spectrum is very different from what I showed you before in two aspects. First of all, for large frequency offsets, it's fine. It's super. So if you are at 2 kilohertz distance, you are in the noise floor. So your CW signal will not disturb others. On the other hand, what I noticed only when I prepared this talk, at small frequency offsets, I do not match the CSI goals. So I thought to myself, why am I so bad here in the middle of the spectrum, while I'm so good at the end of the spectrum. And that is what I showed you. I remind you about the two ramps. I'm good at large offsets because I have this very slow increase at the beginning. And I am bad at small offsets because the race here, so the time to go from 5% to 95% of the amplitude is much smaller for the right function than for the left function. So I said, well, if the rise is faster, let me stretch the right curve. So this is a very interesting graph. In black, you see the original raised cosine profile. In red, you see the inner part of the Blackman-Harris ramp, which is 8 milliseconds wide. So the raised cosine ramp is 5 milliseconds wide. The red ramp is 8 milliseconds wide. This means at the left edge, we are already 1.5 milliseconds after key down. But if you would see such a signal on your oscilloscope, you could not tell one from the other. The rise is the same. And therefore, I said, well, we have to go to an 8 milliseconds wide Blackman-Harris ramp. Then we have an increase, which is almost the same as in the previous case, but it starts earlier, so it has a delay of 1.5 milliseconds, and it has a gradual start, and that makes a good offset at large frequencies. And you see, this one has largely met all our goals. It is good at small offsets, and it is very good at large offsets. However, if you want to sell radios, you want to put a sticker on it. It matches the clean signal initiatives. And if you look very closely, and I will help you, if you look very closely, then at about 150 Hertz and at about 300 Hertz, you have very slight violations. This does not look like a violation, but if you increase the CW speed from 24 to 40 VPM, all these peaks will spread out a little bit, and then this one will cross the mark. So, if you ask me, the 8 millisecond ramp I showed you, it produces a very good signal. The sidebands drop below the noise at about plus minus 1,000 Hertz. That is very good. And at about 150 and 300 Hertz, we have a very slight violation. So what do you have to do if you want to fulfill the CSI marks? If you want to fulfill these prerequisites, you have to make the ramp even a little bit broader. You can do this, of course. This is an example for going to 16 milliseconds, so it's no problem. If you make the ramp broader, you meet this. If you make the ramp infinitely broad, you have a very small spectrum with no information because, then you have a beep. And so if you go to a broad ramp, you can, of course, meet all the prerequisites of the CSI regulation, but you have to go to quite a large ramp of 16 milliseconds. 16 milliseconds overall race time is very large. If you do telegraphy at 40 WPM, at 40 words per minute, your dot length is 30 milliseconds. So the question was for me, if we go broader, we could do so as well as for the raised cosine ramp. So the good old raised cosine ramp implemented in all the FPGA code. So what I did was the following. But this is only simulations, not measurements. I increased the ramp stepwise from 5 to 6 to 7 to 8 to 9 milliseconds until the mask was met. And the result is that for the raised cosine, you have to go to 8 milliseconds. For the Blackman-Harris ramp, you have to go to 30 milliseconds, and then you have it. For 24 words per minute, if you go to 40 words per minute, it's slightly more. But the interesting thing now was, if I compare the ramps which come out of this simulation, where I say I go from 5 to 6 to 7 to 8, and I stop when I meet the criteria. If I then look at the ramp, I learn they are the same. I have the black ramp, the red ramp. Of course, the red ramp is broader. It's 30 milliseconds. I only saw the inner part. This gives additional hints to my conjecture that the raising part, the part where you go from 5 to 95%, determines the spectrum at small offsets, and the slow rise at the ends of the ramp determine what happens at large frequency offsets. Note, if it comes to larger frequencies, the Blackman-Harris ramp beats the raised cosine hands down. I also made a small view graph which shows what happens at 150 hertz. It was a critical frequency, and of course I stopped here because I meet the criteria, but you see also if I go to faster speed, then one of those peaks will move out and hit the ramp. This is what I said, if I go to 16 milliseconds, then I am fine at all speeds. So what does it mean? We have these broad ramps. I show you the pulse as it looks like if I do this broad ramp. The dotted line, you might not see it very well, the dotted line is a hard pulse. The black line is an 8 milliseconds raised cosine ramp, and the red line is a 13 milliseconds Blackman-Harris ramp. And what you see is the black pulse and the red pulse are about the same if it comes to the widths and how they look like. The difference is that the red pulse seems to come a little bit later. Of course, it must come 2.5 milliseconds later. And therefore, my conclusion is, to the radio programmers, use this for the RF pulse, but don't use this for the side tone. Because the side tone, you want minimum delay. So my suggestion to the developers is use a 5 milliseconds raised cosine pulse, as in the old days, for the side tone. And if you can't vary the width, use an 8 milliseconds Blackman-Harris pulse for the RF amplitude. You will not meet the CSI mask at 150 Hertz, but you probably don't care, unless you are a vendor or you need the sticker. Okay? And that's the reason, and that was the original suggestion by Laurence. Let's make the ramp variable. Let the user decide how wide the ramp is. He made an extension to the protocol. 1 bit now says how broad the ramp is. Of course, it's difficult to implement in pure FPGA code. It's easy to implement. It's 5 lines of code. It's easier to implement in all those concepts where you have an FPGA CPU couple, like in the Red Pitaya or like in many other designs. There it's 5 lines of code. And of course, I show you a screenshot from the host software I'm developing on, that's PyHP-SDR. If you go in the CW menu, you see a new point, CW ramp is, and you can go there from 5 to 20 milliseconds, I think, so you can adjust your signal to your needs. But my recommendation is to use an 8 millisecond wide pulse, and this program always does a Blackman-Harris ramp. Of course, this only works if the host program produces the RF pulse. In many designs, RF pulses are exclusively made in the FPGA. This is nonsense. You can easily produce an IQ signal which determines the pulse, but on the new radios, on the Saturn radios, it's now implemented in the firmware. You can get the Blackman-Harris pulses at widths which you like. And also there, Laurence has done the implementation. Also there, the side tone is a fixed width, 5 millisecond raised time, raised cosine ramp, because for the side tone, a CW operator needs minimum latency. I explain this for those not doing CW. If you have a pedal and you want to give a letter V, da-da-da-da, and you have a latency in the side tone, you end up giving numbers which are 4. And many people don't understand why we need this small latency, but that's the reason why we need the small latency in the side tone. I'm afraid with this, it was only a small bit, but I'm afraid with this I'm at the end of my talk. I sum it up. you have to go beyond raised cosine if you are concerned about what happens at larger distances, what happens 1 kilohertz beside your signal. Then raised cosine is not good enough because, technically speaking, the third derivative of coming out is not 0. It's automatically 0 for the other function I showed you. And if you want to meet the ARRL specification, in all cases, you need quite wide pulses. But I think a very good compromise is the 8 millisecond pulse I showed you. And your QSO partner won't notice it when hearing, because the raise from 5 to 95% is the same. So you won't notice a difference on an oscilloscope. The only thing you would notice on a 2-channel oscilloscope is that it comes 1.5 milliseconds later. But this 1.5 milliseconds later comes with a gain. It comes with a small increase which mutes those large offset bumps which you have in the old signal. And I think this is a minimum part of math and technology you should put in your telegraphy transmitter chain. Thank you.
Okay, thank you very much. So it's well, actually, this is a reference to what we've had in the past, where we've had speakers in the past years who said, "Yeah, don't just focus the receivers, because the transmitter also plays an important role," and particularly regarding CW, where you have a very simple signal, this is a very important step where you can approach this optimization question first. So that was a very, very good and very important
this
talk.
is not rocket science. It simply has not been done.
Yeah, and that's even more impressive. Yeah, of course. So, are there any questions?
I have 2 questions. The first one is about the latency. You mentioned that the latency is important for the side tone, but isn't it also important for QSK? So is the limit dependent on the speed?
Yes, you are talking about the key to antenna latency, okay? The side tone is the key to ear latency, and what you are talking is the key to antenna latency. And believe me, there are a lot of contributors to this latency which are far larger than this. It's the block size of the data sent to the transmitter. If you send data in, say, 2K sample blocks, then this gives you a certain latency. If your transmitter chain is a multi-threaded environment where you send out the block which has been computed 3 blocks before, I mean, this 1.5 millisecond is a minor contribution to the overall latency in the SDR radius I am working with.
Okay.
So 1.5 milliseconds, if you could get 1.5 milliseconds key to antenna latency, then you are very good.
Okay, so you say that this latency of little more than 1 millisecond is not so important for the QSK behavior, right?
It is important for QSK, but it's unfortunately only a small part of the latency which you already have.
Okay. Second question is, from former times I remember that the power distribution function is the Fourier transform of the autocorrelation function. So in other words, is it possible to generate the time signal, the shape?
Okay, that is a good point.
Fourier transforming the expected power distribution.
The point is, you can of course take such a signal, then you delete all unwanted peaks, and you do an inverse Fourier transformation. And then you get how your signal should look like.
Yes.
Unfortunately, if you do this for a very narrow signal, you will be reminded of the old times in the 80s where you had 2 narrow audio filters. This makes a very ugly signal, and it's not of the form that you have a raise, then it stays constant, and then you get down. Then you have an overall function for the entire pulse, which depends on the speed. I mean, this is really too much, because I have a very restricted form of the pulse. I start with 0, I have a ramp which is a certain width, then it stays constant, and then I have the same ramp moving down. Unfortunately, if you just take the spectrum, you delete the unwanted peak and do the inverse Fourier transform, the signal is not of that type. It's of that type, which you know from the 80s, if you look at the outcome of a small audio filter, it's a bell shape and then a very peculiar fall off. I mean, it sounds ugly. All those who used narrow audio filters in the 80s know how ugly it sounds. Well, the point is, of course you can optimize the bandwidth to 0, then have your tune signal, but you lost all information. The narrower the bandwidth, the fishier is the signal. You want clear-cut start of the pulse, a clear-cut end of the pulse, and so that is you have to make a compromise here. You have to trade bandwidth versus readability. Does this answer your question?
Mostly, yes. I thought that by modern mathematics, it should be possible
yes,
to
but I tell you what modern mathematics would do.
Program,
modern mathematics would do different thing. Modern mathematics would add here a sinus 8 pi, 10 pi, and 12 pi pulse, and we do a Monte Carlo optimization of these coefficients versus the mask. This can be done. If you want, I can do this. I mean, I'm sure letting a computer run for a week, I get coefficients which have a minimum bandwidth and meet but one would not do the inverse Fourier transform. One would optimize these numbers.
Okay, thank you.
Of course, 3 more to be more flexible.
Thank you. A lot of problems are caused by power amplifiers. What do you expect from power amplifiers?
So you mean I have a very nice signal coming out of my 10-watt SDR, and I feed this into a MOSFET. At the moment, I don't know and I don't care, but in principle, one could do adaptive procedure here as well, but no one has thought about this so far. Because power amplifiers normally have a non-linearity, which is not a problem for a single tone signal like a CW signal, but I have not done a simulation how a power amplifier with a very bad IM3 behavior what this will produce out of my clean signal. I should do this. You are right, I should do this.
Any more questions? No more questions? Then thank you very much, Christoph.